In this video, we're now going to discuss alternating tensor products. And so to start with the definition, let V and W be k vector spaces and small k an integer. Then let's look at the map F from V to the k to W. We call such a thing a k-fold multilinear map if, well, this map eats k vectors in V and spits out a vector in W. It's multilinear if it is a linear map in each of these k slots, if you fix all the other entries. And such a multilinear map is called alternating if it has the additional property that it vanishes on these k vectors here if two of the vectors agree. So if you put 2 times the same thing in 2 different slots, then this map should vanish. And as a remark, a kind of second characterization of being such an alternating multilinear map is as follows. So we observe that if we start with the vector and then we put in the ith and jth column, we put a sum vi plus vj, so 2 times the same, then because f is alternating, this vanishes. But now we use this multilinear property, and so we have a sum of 2 terms here, 2 terms here. If we expand this, then we get 4 terms, which basically have all combinations of the vi's and the vj's, like this. And then you see of these 4 terms, 2 vanish again, because somehow vi, this is 2 times the same thing, this is 0 by alternating property, and the same here with the vj. And so we get overall 0 is the sum of these 2 terms, or in other words, if you now put in vi and vj in slots I and j, then this gives you minus the result of putting first vj and then vi. So if you exchange 2 arguments, you multiply by -1. And you can check this as an equivalent characterization of this alternating property. And you can't just somehow only exchange 2 of these entries, but what you can, of course, do is you can take an arbitrary permutation of the entries. So any sigma in the symmetric group as k. And what does this do? Well, we can write this permutation as a product of such transpositions exchanging exactly 2 things. And for each of these transpositions, then we do it one by one, we exchange these. And then for each of these transpositions, we get a sign -1. So we get a -1 to the number of transpositions. Now, number of transpositions that we need to write the sigma is not unique, but its parity, so its remainder modulo 2 is unique. And this number -1 to this parity is called the sign of the permutation. Maybe you have seen this before. And so overall, we get this plus or -1 term here, depending on the sign of sigma, times f on the unpermuted vectors. So that's a more general statement than this here. So we know what f does if you do an arbitrary permutation of its entries. Let's look at some examples. So one which is very important and which will be used later is that the determinant is such an example. So the determinant takes an n cross n matrix and spits out a number. And you can see this, this set of matrices as kn to the n. For example, this each entry here could be one of the rows. And then you have n rows. So you take the n rows and spit out the determinant of the matrix. So this here would be the vector space V, this would be W, and the determinant is multilinear in the rows. That's one of the properties we know. And it's also alternating because, of course, if you have 2 times the same row, then the matrix cannot have full rank. You have kind of wasted one of the rows there. So the determinant is 0. And so this is the alternating property. And so this is a prime example of such an alternating multilinear map. The second one, which you might know from school or maybe some early classes on vector calculus, is the cross product. So if you have 2 vectors of length 3, then the cross product sends them again to a vector with 3 entries. And these entries are exactly this kind of, for example, the last entry is A1, B2 minus A2, B1. This cross shape of the product, this is why it's called a cross product. And we see here, so first of all, you can check this is this is multilinear. So if you add the second vector A1 prime and so on here, this would go to the sum of the cross products. And it's also alternating. If you put in 2 times the same vector, you can check by hand that you get the 0 vector here. So this is an alternating 2 multilinear map. And one thing we observe here with the motivation that we had from the last video is that the entries here are exactly the maximal minors of this 3×2 matrix, up to maybe a sign here. And so basically up to the sign, these are what we call the Plücker coordinates. And this is the one motivation that I can offer while we talk about these alternating tensor products, because this phenomenon we'll see where it comes from when we discuss later the Plücker embedding in this new fancy language. Okay, but anyway, that's a second example of an alternating bilinear map in this case. And then we have a general definition which says that a k-fold alternating tensor product of V is a k-vector space T here, together with a k-fold alternating map tau from V to the k to T, such that, well, we have one of these universal properties, namely, whenever we have another map to a vector space, which is k-fold alternating, and this map uniquely factors through this T via now a linear map. So somehow this G goes from T to W. And so whatever we give here, we can always factor through this T. So in a certain sense, this is kind of the minimal such alternating tensor product that you can write down. And so we define something via a universal property. So inescapably, you have to follow this up by some existence and uniqueness result. Namely, if you have a vector space V and this K fixed, then there exists a k-fold alternating tensor product as above, and it is unique up to unique isomorphism. And we use the notation T is then called this kind of lambda K V, and then the part of the package is this map from V to the K to T. And instead of writing this map explicitly, what we just do is the image of this map is denoted via such wedges here. So V1 wedge up to Vk. And these are, you see, this is kind of the big wedge here, where all these Vi are elements in the vector space V. And so I'm not going to give the full proof, very similar to Gatman, but you can look at his script there. He gives a reference to some earlier place where he discussed this. Let me just say about the existence part. What can you take for this alternating tensor product? Well, we know that from these k products of V, we have a map to the usual tensor product, V to the tensor k. And this is basically universal k multilinear map. And then to have this additional alternating property, what we want is that whenever such a vector here, so somehow whenever you have V1 up to Vk, such that 2 of them are the same in 2 different slots, we want this to go to 0 in this alternating tensor product, because any k alternating map must vanish on such things. And so what you just do is inside this tensor product here, you look at L, the span of all of these possible tensor products with 2 repeated entries, and then you divide the full tensor product by L, and you call this T. And then here you see you have this K multilinear map, you compose it with this linear projection map, then this tau is still K multilinear map. And so at least this map from here to here is one multilinear map, which is alternating because all of these things here where you repeat two entries are killed. So it is one alternating map, and you can check that any other map must factor through it. And this is then the uniqueness part. Okay. Anyway, so somehow we don't go into details. For now, we just take this for granted. But we are going to now explicitly discuss it when V is a finite dimensional vector space with a given basis. We're going to completely understand what happens here. So this is the next example. Let's say V is such a vector space of dimension n, and E1 up to En is a basis. Then, well, first of all, let's repeat this kind of construction that we had before. So if you have k vectors in V, then we can look at these wedge products where we repeat the Vi plus Vj in the slot I and j. And then, of course, we know this here is 0 because essentially this is in this span of things that we killed by the quotient. And then the same calculation, just repeat the same calculation as above, shows then this property with the permutations, namely that the permuted wedge product is just up to this sign here, plus or minus 1. It's just the unpermuted wedge product here. And this will be important in the next point, because now what is the basis of this k-fold alternating product? Well, for the usual tensor product without alternating property, we know a basis is then just given by taking tensor products of all the basis elements. So we can choose here arbitrary indices of the basis elements. So since we have choice of n different such elements for each of the k slots, we exactly get n to the k many basis elements. Now in the wedge k of V, the claim is that because we divide out something, in general, we will get fewer such basis elements. And the crucial property that we see here, if we replace the tensor here with a wedge, then the order here no longer matters, right? Because up to a sign, we can always shift these things around. So they will no longer be linearly independent. So what we can do if we look at all of these wedges here, what we can do up to a sign, we can always order them. We can always make sure that I1 is less or equal I2 and so on up to less or equal IK. And if one of those things is actually an equal sign, then we would have 2 times the same basis entry here, 2 times the same vector, and this would give 0 by the alternating property here. So all of these actually are not basis elements, but in fact give the 0 element. And so what is left after eliminating these redundant things is that you have these wedge products here, where now the indices are strictly increasing. And by what we just discussed, every element here can be written as a linear combination of such things. This comes from the fact that, well, this here is a surjective map. And so every element in V tensor K could be written as a linear combination here. So any element in this quotient can be written as a linear combination of such things. And by insisting that these indices increase, we have made sure that we don't have any linear dependence between them left. And you can check then that in fact, these are linearly independent. So these give a basis of this alternating tensor product. And then if we ask what is the dimension, well, you see here among the n indices, we basically just are allowed to choose this subset of k elements, and then we have to order it to get this basis element. So we have just n choose k many possibilities, and this is the dimension here. So we have basically understood completely what the basis is here. Now this was pretty abstract, So let's look at a very concrete example. Let's say v is equal to k to the 3, right? And then you have every let's say e1 up to e3 is now the basis, the standard basis. Then any v and w can be written as such linear combinations of the basis elements. And then what happens if we compute their wedge product? Then, well, we just expand this out and I just write a few terms. So for example, this wedge product is also multilinear. And so, for example, the first term is here the A1, E1, E1, E1. So we collect the numbers A1, B1, and then we have E1 wedge E1. In this case, we see, of course, this thing vanishes. The next term doesn't vanish. In fact, the A1, if you combine it with the B2, then you get this term. This turns out not to vanish. And then here you see you get, as the vector part, you get an E1 wedge E2. And then if you pair this term with this term, then you get A2 B1 and this wedge in the opposite order. And then we do exactly here what we discussed in part A. If we switch the order in this wedge product, we get a minus sign. And so overall, if you collect these terms, then you see we can write every such pure wedge product here as the sum of E1 wedge E2, E1 wedge E3, E2 wedge E3 with some coefficients. And you see the coefficients here are exactly, again, these kind of elements of the cross product or these maximal minors of a certain matrix. Okay, so this calculation, if you look at it carefully, shows how you can write all of these wedges here in terms of this basis. And then generalizing this a bit and looking at some of the edge cases, well, if you have wedge 0 of V, then basically the basis is kind of trivial. You have no entries at all. This turns out to just be a number without any vector part. So this is K. Wedge 1, then you have exactly the basis E1 up to En. This is isomorphic to V naturally. And then, well, then the dimension starts increasing basically. And the maximal dimension where this number here is still non-zero is the wedge N of V. And there the dimension is N choose N, which is just 1. So this has 1 dimension by this dimension calculus. And everything can be written as a multiple of E1, wedge E2, wedge E3 up to wedge En. That's the unique basis element. So we know that abstractly, starting with such a wedge product here, we have an isomorphism to K by taking the coefficient of this E1 wedge up to En. And it turns out, and this is what we discuss next, that this isomorphism is exactly the determinant of the matrix formed by these N vectors that we wedge together. But let's not get ahead of ourselves. So this is the content of the next video.